supposed to remind me of air conditioning. If you're sitting there, that's your duty. You can't sit there for free. Not this time I remember. I will forget. What was that? Okay. Oh, this one. Okay. And normally they give me the other one.
No, this one.
Oh, that one. Yeah. That's okay.
No problem.
And also, I don't know what to. There is something I need to launch. And there is something you need to launch on the computer.
Oh, okay.
And I never remember what it was. They always do it.
Oh, okay. No problem.
There is something you always have to launch before the recording, and I never.
It's called Desktop Presenter, so if you just search for it, so hit that, so press start. So it's that one right there.
Okay. So I will just record.
That's it. I'm just going to leave it up for a second so we can see the IP.
Okay. Okay. Okay, so good morning. This question has been on for a while, then disappeared. Now it's on again because we needed to allow the Hollywood crew to do their job. And so now, could you tell me what this force is equal to? You have a spring. The spring has two ends. Both ends move at the yeah. Okay. Okay, I agree with this. I agree with this as well. But I disagree with the last thing you said. It's actually x1 minus x2. Why is x1 minus x2? Because, if you assume that left to right is the positive direction, so the force is positive to the left, x1 is, positive to the right. x1 is positive to the right. x2 is positive to the right. That means that the process process, remember, in this system starts from the left. So it is x1, displacement x1 that results in displacement x2. Or rather, force results in x1, x1 results in x2. So the coordinate system set up like this would require you to write x1 minus x2, not x2 minus x1. Okay. But remember, so far when we were dealing with springs, we always assumed that one end was fixed, and then there was no dilemma. So F equals xk. Very easy. But if you have both ends moving, then you have to just spend a second or two to think, is it x1 minus x2? Is it x2 minus x1? Right, now, lecture 4 today, we are going to, first of all, get familiar with some other systems, because last time we were only talking about components, really. But also some important properties of transfer functions, especially first-order systems, first-order transfer functions. So here is an example. Again, we have a spring and a mass this time. So mass attached to the spring. This surface, we assume there is no friction between the moving mass and this fixed surface. So when you apply Fi, mass is going to move along the x-axis. The other end of the spring is not moving, so this displacement is always 0. So that makes it a bit easier. And as we said earlier, you can write a force equation for the mass regarding the mass as a free body. Then mx double dot will be equal to the difference of the two external forces acting on m, and those would be Fi and Fs, force in the spring. Force in the spring, as we just said, equals to kx. So when you substitute in here, you are going to get mx dot plus kx equals to Fy. If you take a Laplace transform of the left-hand side and on the right-hand side, on the left-hand side you have a second derivative, so you're going to have m times s squared x of s minus s x of 0 and minus x dot of 0. Then you have kx, and you have Fy of s. Now, somewhere here we said that the spring is neither compressed nor extended, so initial condition for x is 0. And we also said that the system is, or the mass is initially at rest, which means the velocity is 0 as well. So before the force is applied, all initial conditions are 0. So therefore, x of 0 is 0, x dot of 0 is 0. Now we get a very simple expression. In the S domain, transfer function by definition is output over input. Therefore, x of s over Fi of s. And that will be 1 over m s squared plus k. Okay. So this is the transfer function. Once again, oh, yes?
Why does the k turn to a capital K?
Did we start with, well, it has been capital K all the time. Which?
Down, lower, like.
Okay. It is a mistake. It's a typo. Yeah, okay. So it's capital everywhere apart from here. So it should be capital, at least for this example. Yeah. So small k, big K, in this particular case is the same. Not necessarily every time. Okay. Right. So this is our transfer function. As we said earlier a few times, now we know if we apply a certain input, we know how to find the output. In this case, to keep it simple, we are going to apply a unit impulse. So a force that lasts for a very short time, and then it becomes 0 again, like a flick. So you flick this spring, this mass attached to a spring. So unit impulse in the S domain will be 1. Output equals transfer function times input. Now, we have the output in the S domain. Let's see what the output is in the time domain. So what we need to do is obviously apply inverse Laplace transform, for which we are going to need the tables. Well, or at least we are first going to check if our particular function exists in the tables. If it does, good, just use the tables. If it doesn't, think what you can do. Partial fractions or something like that. So let's see how our system looks like. It has or our function rather looks like. It has a constant in the numerator, which makes it easy, and the denominator is a second order polynomial. But the first order term is 0, excuse me. So that's what we are looking for. So if you scroll down, okay, the most similar, you can keep searching, but the most similar example is actually this, case 10. So in the denominator, you have a second order term and 0 order term, and there is no first order term. That's what we want. But the numerator doesn't have 1, it has a constant. It has an omega. Now, but what is omega? Omega is the square root of this coefficient here. So the 0 order term in the denominator is omega squared. This one has to be omega. So we have to make sure our function looks exactly like this one before we can apply the inverse Laplace transform using the tables. Over here, this is our, sorry. First thing, I forgot that. First thing, this coefficient has to be 1. That's the first thing you have to do. Then compare the coefficients. In our case, this is not 1, this is m. So we divide by m both the numerator and the denominator here. So as a result, we get s squared. The coefficient with s squared is 1. That is what we have here. Now we want to adjust these coefficients according to what we have in the tables. So omega n squared in our case is k over m. So here we want to have square root of k over m. Since we don't have that, we have to, well, we create it first, square root over k over m. But then to make it the same as what we have over here, we have to divide by square root of mk. Okay. So now you see this is the same thing because square root k and square root k will cancel. Square root m times square root m will be m. However, this highlighted part will be left outside of the transform. It is a constant, so we leave it outside. And what is left here is now exactly what we have here. So we check on the left-hand side, and our time domain expression is sine omega t. So this constant times sine omega is square root k over m times t. So the answer is, when you have a mass and a spring, and you apply an impulse force, our mass is going to oscillate. There will be a sinusoidal function with a constant amplitude and the frequency that will depend on the stiffness of the spring and the mass attached to that spring. Okay. Let's leave this output at here and get back to the transfer function. Transfer function can have two standard forms and a million non-standard forms. The first standard form is when the last coefficient in the denominator, the coefficient with s to the power of 0, if that coefficient equals to 1, we call this form non-dimensional form. Or normalized form, as we already know, is the one where the coefficient with the highest order term, in this case s squared, equals to 1. This is what we call normalized form. And I mentioned a few times, all functions in the Laplace transform tables are in the normalized form. So if you want to use the tables, first thing you do, normalize your transfer function. Okay. Another advantage of normalizing transfer function, you can immediately see what the roots are, root of the denominator are. In this case, there will be 2 roots plus minus square root of minus km. But what is the relevance of the non-dimensional form? We'll take slightly a different transfer function. Still second order, but it will have 2 real roots in the denominator for a change. Okay, so if the transfer function has this form, capital A over S plus A, S plus B, this is obviously normalized. If you make it non-dimensional, then we have to divide by AB, both the numerator and denominator. Then in the numerator, you get capital A over small ab. In the denominator, you have S over A plus 1, S over B plus 1. Here, we are introducing now some new terminology that you should familiarize yourself with. This constant here, A over AB, is what we call steady state gain or DC gain of the system. These constants here, 1 over A and 1 over B, are called time constants of the system. And today, we are going to see what time constants really are, why they are so important. So in the non-dimensional form, you can directly read the values of time constants and the value of the steady state gain or DC gain. Okay. Let's see first quickly, very quickly, what a DC gain is, steady state gain is. Steady state gain is relevant in the steady state case, when time equals to infinity. Okay, so it describes what the system does at infinity, when time is infinity. And it actually represents a ratio of the value of the output divided by the value of the input at infinity. At infinity. Okay. So if you apply a step input, unit step input, what is the value of the unit step when time is infinity? What is the value of the unit step function when time is infinity? 1. Okay, thank you. Now, if you apply unit step, multiplying this transfer function, where is it? This one here, or this one here for that matter, doesn't matter. So the steady state value of the output can be obtained by finding the limit when S approaches 0 of S times output. Output, remember, transfer function times input. Now, finding this limit shouldn't be too difficult. S and 1 over S will cancel each other. You have A, capital A, S is 0, S is 0. So you have A over AB. So input at infinity is 1. Output at infinity is A over AB. The ratio of the two is A over AB, simply because the other one is 1. So it shows you how much the system augments the input. Apply input. Let's see if the output is going to be greater or smaller, and by what factor it is going to be greater or lower. Only at infinity. So steady state gain is not concerned with the transient process, only infinity. Time constants are very important when it comes to the transient process, how the system gets to infinity. Okay. We have another example before we actually get to see what time constants are. At this stage, please accept just the very descriptive definition of time constants. Time constants tell us how fast the system is, how fast the response is. So when you apply an input, how quickly the system reacts to that input. Let's leave it at that stage. Now let's take another example because it is also giving us something interesting. Let's have a mass attached to a spring and a viscous damper for a change. So it is a spring mass damper system. And we assume this whole thing is happening in the vertical plane. So when you attach this mass to a spring before your process starts, so you're just creating this system, assembling the system. So you have a mass, you have a damper. You attach the mass, the spring will expand because of the weight of this mass. How much it will expand? By x naught. So this length x naught is the initial expansion of the spring due to the weight of the mass. Okay. So now let's write a differential equation describing this system. So sorry, now you are applying the input Fi. And as a result, mass will move along this x-axis. So the displacement will be x plus x naught, which was the initial displacement. So force analysis. The forces acting on this object is Fi. If you take the downward direction as positive, so you have Fi rather, and you have the weight of this mass, mg. The forces resisting the displacement will be the force in the spring, which is kx plus x naught. Remember, initial displacement of the spring is x naught, so there is a force already acting upwards, kx naught. But this time, if you move x even further, the force will be x plus x naught. And the other force acting against the, displacement is the force in the viscous damper. The force in the viscous damper is proportional to the relative velocity between the piston and the cylinder. Okay, so it is c times x dot plus x dot naught. So these are external forces. When you put them together, you get inertia. So m equals x dot plus x naught. X double dot, sorry, plus x naught double dot. Now, x naught is a constant. So it is a one-off displacement, which depends only on the weight or mass of the object and the stiffness of the spring. They are both constant. So this is going to be 0. So will this as well. Second derivative of a constant is definitely 0. So we have Fi plus kx naught minus mg, and now you have these two derivatives. But remember what kx naught was. Kx naught equals to mg. mg was the initial force, the weight of that block that resulted in the extension of x naught. So mg equals kx naught. So you can very easily get rid of these two terms. Sorry. So this is the differential equation describing this system. So you can see that gravity plays no role in creating the transfer function. Or, as we said a few times, initial conditions are irrelevant when you are creating transfer function. But this is how you make sure initial conditions are irrelevant. Or you can explain, there is a third way to explain what is happening here, that we are actually working in terms of incremental variables, not absolute variables. Because x is measured from when the mass is at rest. That is the most convenient place for our coordinate system. Not somewhere up here when the spring is uncompressed or unextended. Because this particular point is not really relevant for our system. The process starts here when the mass is here, and then you apply the force. So we moved the the origin of the coordinate system from wherever the spring was in the neutral position to where the process starts. What we also did, we don't take the total force acting on this mass, Fi plus weight plus mg. We also use incremental force that starts from mg, right? Sorry. So the force starts from mg and then becomes whatever function it is. So both Fi and x are actually incremental variables here. Okay. Now transfer function becomes, getting transfer function is easy. Laplace transform of the left-hand side equals Laplace transform of the right-hand side, assuming initial conditions to be 0. Here is the transfer function, in this case normalized. The DC gain, what is the DC gain of this transfer function? Well, if you read this, you know the answer. But DC gain is, you can read the DC gain from the numerator if the denominator is non-dimensional. But it is not. So you need to non-dimensionalize the denominator, meaning divide by k. You want this to be 1. So when you divide by k, you will get 1 over k up here. This is not the DC gain because this is normalized, not non-dimensionalized. So it's 1 over k. Okay? So at infinity, x will be equal to 1 over k Fi, which is what we know. Now time constants. First, let's start with an electrical system. Electrical circuit containing a resistor like this and a capacitor like this. So input voltage is EI, output voltage is, it's not EI, it's E1, sorry, and output voltage E2. And then as a result of voltage EI applied, you have current I going through this loop. So E1 will be equal to voltage across the resistor, which is IR, plus voltage across the capacitor, which is E2. That's the first equation. The current through the capacitor will be equal to C E2 dot. Okay, that's capacitor. So this system, at least in this early stage, is described by two differential equations. Sometimes we can't immediately write one differential equation that describes our system. If the system, the more complex the system, the more those equations you're going to need in order to describe the system. In which case, we'll have to introduce what we call intermediate variables. In this case, it would be current. So to easier model our system, we have to include this current. But the good news is that between these two differential equations, we can eliminate I and end up with voltage 1 and voltage 2 and their derivatives. Because our differential equation can contain only two variables, input and output, if you want to create a transfer function. If you have a third variable, something is wrong. Transfer function is output or input. And a third variable will not make it possible to create the transfer function. Okay, so when you are modeling a complex system, you are going to write n plus 1, if you are writing n equations, you can have n plus 1 variables. So when you eliminate n variables, you end up with one equation with two variables. One equation with two variables. Remember, you're not solving simultaneous equations. You are creating a mathematical model. So over here, this is one differential equation with two variables, input and output. The derivatives count as the variable itself, x and f. So that's what we want here. We want E1 and E2. So eliminating I, Now, this is very simple. You get this equation, this differential equation. Finding Laplace transform, assuming 0 initial conditions, we'll have on the left-hand side RCS plus 1 times E2S. On the right-hand side, you have only E1 of S. Output over input give us 1 over RCS. Remember what we, a few minutes ago, what we said about the DC gain and time constants. The DC gain of this, first of all, is this normalized, is this non-dimensional? Non-dimensional because this is 1. This last coefficient is 1. So the DC gain is 1, or steady state gain is 1. And the time constant is RC. RC. Because RC multiplies S. Okay. How many time constants does this system have? 1. Because this is a first-order system. What does it mean, the first-order system? That means that the transfer function is of the first order. What does it mean that the transfer function is of the first order? Because the polynomial in the denominator is a first-order polynomial. So, the time constant RC. Now, let's see if we apply a unit step. So if you apply a unit step as the input, then the output becomes transfer function times 1 over S. We need to normalize, if you want to use the tables, divide by RC, the numerator and denominator. Check the tables. Okay. Here it is. So case 14. 1 over S, S plus A. And this is what you will have in the time domain. So case 14 will give us that output voltage will be equal to 1 minus e to the minus t over RC. So input is a unit step. So the voltage suddenly jumps to 1 and stays there. What does the output voltage do? Doesn't jump straight away. It exponentially approaches 1 in this case. So the input is 0 and then jumps to 1. That's voltage E1. This is voltage E2, which is this particular exponential function. Okay. Now, this exponential function doesn't have any particular, obvious points that we can use to define this exponential function. The only thing we have is this product RC. And RC is the time constant, as defined earlier. What it means in this particular case is that when time reaches RC, when time reaches tau, the output changes by 63% of its maximum value. Okay. So this shows you how quickly the system responds. Well, if this tau is short, so you have very steep exponential function, we say that this system is fast or quick. It reacts quickly. If time constant is long, if it is a big value, then it may take very long until it reaches 63% of its final value. And this is why the time constant is the measure of how fast the system is. We can't ask ourselves how long does it take for the output to reach infinity, to reach the steady state value. Well, it never really reaches steady state value. It reaches it at infinity. So you can't use that as a measure. So the measure of how fast the system is the time constant. Okay. Yeah? Is
there a reason why you choose 63%?
No, I didn't choose it. I didn't choose it. It was someone else. I didn't claim, I didn't, reference the source. But see, if time equals RC, then you have T over T, which is 1, or RC over RC, rather. So e to the minus 1 is 2 point whatever. Find the reciprocal value, then 1 minus that will be 0.63. Yeah, I wish I invented this, but it was obvious someone who did a few hundred years ago. Yeah, so it is simply a matter of mathematics, substituting the value of the time constant for t, and you will get 0.63. Just if anyone has a calculator, you can quickly check that. Okay. And we know from experience that electrical systems will have a very quick response. So a circuit like that will very, very quickly respond to a step input. Okay, so this tau will be probably measured in milliseconds. Let's take a water tank system. So you have a water tank, you have a pipe bringing water at the volume rate Qi, but the tank is also losing water through this valve at the rate Qo. The height of the tank is h. The outside pressure is Pa, or atmospheric pressure. Okay, first of all, the flow through the valve, Qo, will be proportional to the pressure difference. So K is the valve characteristics. Delta P is the difference between pressure before and pressure after the valve. Pressure before the valve will be equal to the hydrostatic pressure due to the height of water plus atmospheric pressure acting on the surface of water. So this is the pressure before the valve, Pa, atmospheric pressure, plus hydrostatic, which is rho gh, minus the pressure outside, on the pressure downstream from the valve is atmospheric pressure, Pa. So minus Pa and plus Pa will cancel each other. So flow through the valve, or the outflow from the tank, will be equal to K rho gh, where the only variable is h. Height changes as Qi changes or Qo changes. Since these three constants are constants, we are going to replace them with 1 over r. So with only one letter. And why do we use r? Because that resembles resistance in electrical system. So it is easier to compare. Easier to compare two systems that are completely different, electrical and the fluid system. So we can say eventually that Qi equals h over r. So that is our first equation. And second equation we can write is, if you remember our last lecture, the flow in minus flow out equals the rate of change. In this rate of change of mass, or in this case volume, because we are ignoring compressibility of water. Naturally, yes? First one, this one. From this, if Qo equals a constant times h, okay, so this is a constant. So instead of Q rho g, I'm using 1 over r. It's really clumsy carrying around those three letters throughout all these equations. So I will have only one letter. And that letter, as I said, resembles electrical resistance. Okay. And this one is simply balancing the flows into the tank, into and out of the tank. So Qi is the flow in. Qo is the flow out of the tank. The difference between the two will result in change in volume inside the tank. But if you assume that cross-section area is constant, so it is a cylindrical or rectangle, doesn't matter, but tank that has a constant cross-section area along its height, then A is constant, so it is h dot, A times h dot. So now we have two equations with three variables, Qo, Qi, and h. Exactly what we want. We want to eliminate the variable we don't want. Okay. The only question is, which one is the variable we don't want? Well, we either have to listen to someone who tells us we don't want that variable, or you have this system for a particular reason. There is a particular application. And usually what you have in some manufacturing processes is that you want a constant height. So you're interested whether how this height behaves, in which case height is the output. So don't be confused. Output is not necessarily something that leaves physically the system, is getting out of the system. Output is the variable that you are interested in. the variable you want to control, the variable you want to observe, the variable that has a meaning to you. So if height is what you want to control, this is going to be your output. But someone else may be more interested in the flow, rate of flow out of the tank. To them, QO would be the output. So if H is the output, QO is the input, then, sorry, QI is the input, QI is the input, then let's get rid of QO. So if we do that, this is our differential equation. This is the mathematical model that describes our tank. Okay. Now it becomes easy. Laplace transform of the left-hand side equals Laplace transform of the right-hand side. You get HOS, you get QIOS. Find the ratio. It's 1 over AS plus 1 on R. This is neither normalized nor non-dimensional. So we can write it either like this, so it is non-dimensional, or write it like this, so it is normalized. Again, let's apply unit step input. So the output in the S domain is transfer function times input. Of course, this has to be normalized if you want to apply the tables. But the case from the tables will be exactly the same as the previous one. The only difference is this R here. And because of R here, our output is going to have R multiplying this exponential function. Yes? Volume rate. Q by, the convention is the Q is cubic meters per second. M dot would be kilograms per second. However, because this is a liquid, we assume there is no compressibility, so it would be, the result would be the same if you assume this was a mass flow. It's different with gases, but the liquids, no difference. It's just an additional row you're going to have. Okay, now this function is almost the same as the one we had in the electrical system, apart from that constant R multiplying the expression for the output. And that means, in this particular case, that our output is, again, the exponential function, but the steady state value will be R, not 1. Okay. That makes the steady state gain equal to R. Because remember, this is the input. At infinity, the value of the input is 1. The value of the output is R. Output over input at infinity is R over 1, which is R. So the steady state gain is not 1 in this case. It is R, whatever the value it could be. We assume here that R is less than 1. Time constant. The time constant of this system is AR. That means that when time reaches the value of AR, the output will reach 0.63 of R. Not just 0.63, but 63 of the maximum value, which is R. So 63% of R. Okay. And finally, a thermometer. Let's make a mathematical model of a thermometer. Very simple one. It's a spherical glass bulb with mercury in there. And you have some constants given here. Glass has conductivity K, and the mercury itself, it has its density, or specific density. It has its specific heat, and the sphere has a volume V. Theta1 is the temperature outside this. So if this is a hot fluid of some sort, first the temperature is held outside, held in the atmosphere at temperature theta1 rather. And then it is placed into the thermometer where the temperature is theta O. Bath, as they call it. Okay. What you're interested in, we know that eventually the temperature, the thermometer will show theta O. The thermometer will show what is the temperature of the surrounding fluid. But we are much more interested in the dynamics, how the thermometer reaches, how the mercury reaches that value that we all want to measure. Okay, so once you place your thermometer inside the hot fluid, then what will happen is that heat will flow through the glass wall and heat the mercury in there. As a result, the mercury will expand and move up the scale here. Okay. So what we want to write here is an equation of thermal balance. So if this sphere is our control volume, we identify all rates of heat in. But there is only one. There's the heat from the hot water towards the mercury inside the bulb. Heat out, there is no heat out. We'll simply ignore. There is a very small amount of mercury getting out of the hot water, taking out some heat, but it's so minimal that we'll ignore it. So that means that the rate of heat in will be equal to rate of change of heat inside our volume. Rate of heat in is actually the conductivity heat, which will be equal, if you remember from the previous class, minus Ka over d. K is the conductivity of glass. A is the area, surface area of the volume, and d is the thickness of the wall, times d theta by dx. However, this equation is true, but it's not very useful, because we are not interested in how the temperature continuously changes along the thickness of the wall. That's not our problem here. So we'll rewrite this equation in so-called discrete form. We are only interested in temperatures on one side of the wall and the other side of the wall. That's all. Okay. And internal energy, the rate of change of internal heat, is this, rho Cv theta dot, where theta is the temperature of the mercury. These two heats have to be the same, as we said earlier. So this will give us this equation. What is made confusing here in this example, I didn't do it. What is made confusing is that theta O, in this case, is not the output, it is the input. If you think about the thermometer, what is driving the heat to enter thermometer is external temperature, theta O. Output is theta, temperature of mercury, in this case, temperature inside the thermometer. Okay. Now we can make few simplifications. First of all, it's known for a sphere that A over V is approximately equal to 3 over R. Not approximately, is equal to 3 over R. And also, once we make that simplification, we can also get rid of all these constants and just call them alpha. So alpha is 3K over rho C dr. Okay? And that will give us theta dot plus alpha theta, because we have minus minus, plus alpha theta. And this minus moves to the right-hand side, so it is plus alpha theta O. Laplace transform, left-hand side, right-hand side. This derivative will give us this term here, corresponding to the initial value. And if you leave it like this, so whatever the ambient temperature was, 20 degrees, if you leave that 20 degrees, even if you convert that into Kelvin, you can't create a transfer function, because you can't create the ratio of theta and theta O, because this term doesn't contain theta, doesn't contain theta O. It is just a constant, just 20 degrees Celsius. So in this case, you don't have a choice. You have to use incremental variables. You have to convert all your temperatures into incremental temperatures. So you measure temperatures relative to the ambient temperature. If it happens to be 20, that's your zero. That's your temporary zero. That's your zero only for solving this particular problem. And you have to do it. Otherwise, you are stuck. This is where you finish your your work. So you make this 0. Remembering later on that all temperatures were measured from 20, not from 0 Celsius, or definitely not from 0 Kelvin. If this is 0, the transfer function is easy. It's alpha over S plus alpha. Okay, we may be just a couple of minutes longer than usual. Now, let's assume a step input, but not a unit step input. The magnitude of step input is theta b. So theta b is a constant. But theta b really is the difference between outside temperature and temperature of the hot fluid. How do you understand the input is a step function? Remember, a step means a sudden change from 0 to theta b in this case. Sudden change, and then it stays constant again. So how, in this particular case, how does it look like? Yeah. That's right. Have you heard this? So your thermometer is outside the hot tub, and then you just plunge it. So you quickly push it in. That's what makes it a step function. There is no particular reason in real life why would you make sure it's so quick. You may burn yourself. You can put it inside any way you want. But for analytical purpose, to make it easier for us to analyze, we assume it is a step. It is a sudden change in temperature. So suddenly the temperature surrounding the thermometer changes from whatever we have in the room to whatever we have in that fluid, hot fluid. Okay. The rest is the same. You multiply the transfer function with the input. Therefore, you have S here, but you also have theta b up here, the magnitude of the step. Find the inverse Laplace transform. And again, you have a very similar exponential function for your output, apart from you have this theta b, because your input is not a unit step. Rather, it has a magnitude, your step has magnitude theta b. Okay, if you take some typical values for a thermometer, for glass and for mercury, we'll find out that the time constant, alpha in this case, is 0.56 seconds, so half a second. Okay, and the graph, okay, we have everything here. So this exponential function, the graph would look like this. Steady state value, theta b. So it starts from 0, approaches theta b, and when it reaches the value of, when the time reaches the value of the time constant, which is in our case 0.56, we will get 63% of the steady state value, which means you dip your thermometer, after half a second, it will show 63% of the actual temperature in the dish. So you have to wait. Yeah. It's usually regarded 5 times that, 5 times the time constant, until you can regard that the output is equal to its steady state value. 2.5 seconds altogether is not much. I still don't know. When I was a kid and my mom suspected I had the flu or whatever, she would ask me to keep the thermometer under, usually left, I know why, left armpit, and to stay steady, you know, for 5 minutes. Why 5 minutes, I don't know. But anyway, I know what moms do today. Anyway, so I hope this lecture explains what the time constants are, what is the relevance of time constants. All these systems are only first-order systems. They all have only one time constant, so they're selected that way. Also, we touched on the steady state gain. What is the relevance of the steady state gain? Any questions? Okay, thank you. Now we have the tutorial. I will really have to ask every third row to be empty. It's okay on this side, but over here. Otherwise, if you can't reach everyone, what's the point of, of you doing that? I mean, unless you like it that way. Okay. I didn't have time before. But also,
Recently, long questions. There were lots of questions from me. Today, everybody's going to. Student is going to ask, I'm going to say, oh, what the bus is going to be like. That's in Q2 I was making so many calculation errors. Like every time the students point out the Laplace transform is wrong, there's a calculation error. No,
based on this one, right? Thank you.
first of all, yes. And they both show how big the system is, how slow it is. They are very different. They are very different. Then the slowest one that we take our part. Because to take it to exponential, we have a try each with a large number. Longer than this, because one that lasts longer dominates. very quickly zero. Yes, but then you don't have a function. Then you have different parameters.
有的，但是你知道的，我没有。
Have sinusoidal responses. We'll talk about that as well. So everything set so far applies to exponential. You're not expecting, if you remember the definition, you want to use it, you don't have problems. But we are giving you tables so you don't have to solve those equations. That's the idea. Oh, I put the announcement on Moodle. Lectures 1 to 5 or sets 1 to 2. Just check the announcement, not forum, but the announcement. Should have.
上面的那些求到什么？ 因为你知道为什么？因为当时的R的3大概是
Okay.
Yes, I think when we want to find the transfer function, I thought that maybe we should use initial conditions for the
Transfer function assumes zero initial.
yeah. So
But the output, if the output is based on non-zero initial conditions, then you can't use the transfer function. You have to go back to the differential equation and find the output.
so the transfer function uses zero initial condition.
Yes. Yours. Yeah. You see what I did? Have you been to the lecture? That temperature, was really sticking out. I was unable to create a transfer function because of that initial value of the temperature. So I said, okay, that's going to be my zero. So actually, even if initial conditions are not zero, I force them to be zero by moving my coordinate system. Okay. But that means when I show this graph, that zero is not really zero. It's the zero. It's not 0 Celsius. It is the zero I adopted. It's maybe 20 degrees, which is the room temperature. But it has to be zero. You can't create a transfer function unless you have zero initial.
You don't call that transfer.
Sorry?
You don't call that transfer function.
No, I was unable to create it. If you remember, I still have the lecture. Where was it? Here. I couldn't put all terms with theta on one side and all terms with theta O on the other side because I have this constant. It's just a constant. It has no theta or no theta O. No input, no output. So I can't create that ratio of two polynomials. Okay. So this has to be zero if I want to create a transfer function. But before I just say it is zero, I have to think, okay, what does it mean? That means that all temperatures will be measured from whatever room temperature is. Relative, so they will go up or down, it doesn't matter, but that's our reference. It's the reference temperature. That's it.
What other cases exist such as this one? The example.
Yeah, well, we just said with this spring and displacement. Okay, so I said this is going to be zero. Okay, so x naught doesn't interest me. Wherever x naught is, I will call it zero. Okay, and also mg doesn't interest me. So the only force that interests me is Fi, which is added on top of the weight. The weight already exists. If you have initial conditions, transfer function will not help you. If you want to find the output. If you have initial conditions, you have to use the differential equations. Do Laplace transform including the initial conditions. The output has to be whatever input has to be whatever input is given, and then you get C as a function S, which is the output.
In this case, strictly the solid
You can't. You can't. If you have initial conditions, you can't.
in the exam, like, I don't know which one maybe apply.
Well, now you know. I just explained.
Yeah. What is other cases?
Well, I can't think of a third case.
Government exam. Is that in a condition?
Yes.
Because the technical
But it will be in the form of n, you know, so n derivative and then
Oh, yeah.
the most general.
Because in the quiz you just provide. Okay.
Okay. You know, they were very smart.
Okay.
So I want to understand, is there any way that we can determine which one is our input and which one?
You have to understand the system. What initiates the whole process is the input. What is the variable interest to you is your output.
That's what I'm like.
So, for example, a spring mass system. Nothing will happen until you apply the force. So the force is input. And then you observe the output, which is X.
Okay.
It is a bit more difficult, say, with the thermal, with this system. What is the input, what is the output? Well, first of all, we said we want to observe the dynamics of temperature inside the thermometer, of how the mercury moves. So that is our output, that's what we want to observe. That is output of the process.
Yeah.
Now, what is the input? Why would the mercury move? Because there is an external temperature. So the temperature starts the process, and we are describing that process. So that external temperature is input.
So here theta and theta zero and everything about theta are the temperature.
Sorry?
Theta, what
Yes.
is theta? Is theta temperature?
Yes.
Okay.
Temperature of the hot water.
And here, why we set theta zero as zero?
Okay, I just thought maybe you should do this. Because if I don't say that, I can't create the transfer function.
Yes.
Okay. So, then I said that theta of zero is, for example, 20 degrees Celsius. That's where the temperature of the thermometer before I put it into hot water. So that 20 degrees is what I'm going to call zero. So that's my zero. But it's not really 0 degrees Celsius, it is just zero. It is just a reference temperature for this particular problem. If I don't do it, I can't solve that problem. I can't create the transfer function. So we said, when you were doing set 2, down here we said, for transfer function, ignore initial conditions.
Yes.
Okay, down here. When you're solving these problems, okay, if you want to find the output, you have to include the initial conditions. If you want to find the transfer function, you assume they are all zero. Okay, but this is an example how I do it. I don't just say they are zero. I say room temperature is my reference temperature, my datum temperature. Therefore, I call it zero. Okay. But when I do that, that means that this graph, this is not zero. This is the room temperature. So I'm measuring relative to whatever zero I selected. Okay. So this is not 0 degrees Celsius. This is just whatever the room temperature was. Like as I said, the height of the table measured from the floor, and I don't care how high the floor is. To me, that is the reference. Like in this case, in this particular problem, the room temperature is the reference. Okay.
And on the graph, every every graph that we
Yeah.
look at, we look at it in the lecture,
Yeah.
like this one.
Yeah.
You said that's one time constant.
Yeah.
From that 11 I learned that it's going to complete the charge or something for the first circuit to take 5 times constant.
Well, that is, but that's more like a conventional rule. It's not. There's nothing mathematical there. We just said time constant times 5, and we can say now we are here. No, we reached the steady state. Mathematically, we never reach steady state. There's always a little bit missing. But yeah, in practical terms, it's about 5 times.
That can apply to every system.
Yeah. Okay.
Thank you.
Okay. More questions.
It's from tutorial, and then there's the graph like this, and up to this far you can get it, but it's like this one is combination of step and then downward, is it, or should I just
Okay.
Yeah.
So you have your first is this positive ramp.
get
Then you have a negative ramp, but you shifted by 1.5. Then you have a negative step, magnitude 10, shifted by 3. I agree with that. Then you have positive ramp. Then you find the gradient. Is this 5? Really?
yeah,
No,
like
no,
a rise,
it's 4.7. Oh,
rise,
okay.
rise of one. Oh wait, that's some. Sorry.
Yeah. Okay, that's better. Okay. And finally, you have a negative ramp here. Do you have it? Yeah, you have the same. You just change this coefficient. Yeah, and shifted by 7.7. Yeah, that looks fine to me.
Oh, okay. So yeah.
I would still like to see how you write it analytically in the other way.
Oh, okay. Yeah.
Yes. No. There is an answer on all of them. No. Lectures 3, 4, and 5 are all in the same thing. Set 3 cover 3. Set 1 to 3 lecture.
次你一说中文，我就想起来这一次我们去那个乌里斯这个他在这个就是翻译他的经验，他在给学生讲这个这个肉，这个肉。
Yeah,
Because otherwise they can start.
I don't know if I'll need the sheet my sheet though. I don't know if I'll need it or not. Because I think I'm taking a Friday Monday off and I'm on Friday. So I should see. But if you need me to replace it, I'll have to.
Okay, so that I will do. Like, I thought if you are also going on then we could just start it, but yeah, then it's fine.
I haven't decided yet, so I'll let you know.
Yeah, I'm taking a vacation in week 13, so I still have a lot.
Your card already